So in here we will have, since the probability of a boy is 0.75, I'll just write it as 3/4 so I don't have to pull out the calculator, but this will be 3 times 3 is 9/16. So it'll be 9/16 chance of having 2 boys, so a little bit more than half. A boy and a girl would be 3/4 times 1/4, which is equal to 3/16. And then a boy and a girl would also be 3/16. That would just be this in reverse. And a girl would be 1/4 times 1/4, which is equal to 1/16. So again, one thing you'll notice is that 9 plus 3 is 12, plus 3 is 15, plus 1 is 16, and 16/16 is equal to 1. So we again get the same probability space, but keep in mind that it's not just a 1/4 probability that you get a boy and then a boy, or a girl and then a girl, or a girl and then a boy, etc. Let's consider one more example. Suppose that we roll a die, and you want to know, you roll it twice, and you want to know the probability of getting an even on the first roll and an even on the second roll. Okay, well, if you look at the die, there are 6 possibilities. So I'll just call this probability of even. There are 6 possibilities, and 3 out of those 6 are even numbers. So you have 2, you have 4, and you have 6. Okay, so again you come through here and you say, alright, well, if I roll the die once and I roll it again, the 2 outcomes should be independent of one another. The fact that I got an even the first time around should not affect the fact that I get an even the second time around. By the way, I'm just using these subscripts to indicate, just to keep it clear that we're getting an even first and an even second. Okay, so the probability of an even is 3/6. The probability of an even is 3/6, which if you multiply that before you reduce it, you get 9/36, and that reduces down to 1/4, or 0.25. So you've reduced your overall likelihood. Originally it was 1/2, but you took 1/2 of 1/2, and you got a quarter. Well, how do we justify this? In other words, is there a meaning for 9/36? Well, if you draw yourself another little table, again, very handy-dandy little tool. Other ways you could do it as well, but we'll just discuss this one here. So I'm going to list the die 1 possibilities and the die 2 possibilities. Again, 1 through 6. So if I now create columns for every die 2 outcome, and I create rows for every die 1 outcome, what you're going to notice is that every single box represents a combination of die 1 and die 2. So like this square would be die 1 is a 1, die 2 is a 1. Now if I actually go in here, first of all I see that this is the area of this thing is 6 long by 6 wide, and that's a total of 36 different entries. Hey look, there's a 36. Now obviously die 1 can't be 1 because that's an odd number. That wouldn't satisfy what I want. But 2/2, a 2/4, and a 2/6 would work. A 4/2, a 4/4, and a 4/6 would work. A 6/2, a 6/4, and a 6/6 would work. Well, if you look at that, that's 3 possibilities here, 3 possibilities, by 3 possibilities here. Well, if you were to condense all these little shaded cubes together, you'd have a 3 by 3, which would be a total of 9 squares. So in this case, these numerator and denominator actually do have meanings. This is the size of our sample space. This is the number of ways we can get what we want. So that lends itself to some ideas behind why the joint probability formula works. Okay, let's jump to another one. Let's take a look at this guy here. So according to the U.S. Statistical Abstract, the probability that a traditional married couple, both aged 80, live to age 81 is 47.9% for the male, 62% for the female. So big difference there. Assuming the survival of one of the two is independent of the survival of the other, find the probability that they both survive to see age 81. Neither survives to see age 81, and the wife survives and the husband dies. Well, this may seem overwhelming given that there's so many things to find. But guess what? If you put it in a table, the work is almost effortless. So let me represent M to say male survives, and male with a bar over the top to say that the male does not survive. So this is a sign that means not, or does not. So it's not in the survival set. And similarly, I'll do the same thing for female. Well, we know that the probability that a male survives is 0.479. So I'm going to put 0.479 over here, and I know that this all has to add up to 1.